So in this chapter, we're looking at two types of thermodynamic properties. And we're looking at two thermodynamic properties in this chapter, entropy and Gibbs free energy. We also will look at delta H, which is something that if you've taken General Chemistry 1 recently, you talk about how to calculate delta H. And so when we're talking about entropy, we're talking about disorder. So the more entropic something is, the more disorder it has. So the way to think of disorder is the more disorder something is, the more spread out the energy is of that substance that we're looking at. So for example, if you have a deck of cards and then you throw the deck of cards on the floor, the stack of cards is less disorder than when the cards are thrown all over the floor because the energy is spread out. There's more disorder, so therefore it's more entropic. And one of the laws of thermodynamics states that everything in the universe tends to disorder. So that's the normal progression of things is towards disorder. So it takes energy to keep things in order. And so depending on the physical states, we can see how the progression of energy is dispersed. So for example, as we go from a solid to a liquid to a gas, gas is the most entropic physical state. So if you have something in liquid form, something in gaseous form, the gas is going to be more entropic, more disorder. Because remember, gas molecules are more spread out, energy is more spread out, so it's more disorder. So in the first example, we have CO2 liquid, CO2 gas. Since the gaseous state, the energy is more spread out, it'll be more entropic, more disorder than CO2 liquid. Now with B, we have two different types of oxygen. We have ozone and we have O2. We'll get to liquid and aqueous in just a moment. So with O3 and O2, we have to look at the structures of these. And if we look at O3, the Lewis structure looks like this. And O2 looks like this. So these are the difference in the Lewis structures of O2 and O3. And so what we're looking at here is we're looking to see which one has more degrees of freedom. So what does that mean? It means it's more flexible molecule, because if it's more degrees of freedom, it has more ways to rotate. So when you have ozone O3, you see you have 3 atoms. Now these bonds can bend, they can stretch, and so you have more bending allowed when you have 3 atoms versus when you have 2 atoms. So the only thing that this O2 molecule can do is the bonds can stretch. Whereas if you have 3 atoms in a molecule, now the bonds can stretch, the bonds can bend. So ozone is has more degrees of freedom. So ozone would be more disordered because it can move around more than O2. O2 is constrained because it only has 2 atoms. And so here ozone would be more entropic than O2. Next we have an aqueous and a solid species. And generally with aqueous species, so we write a simple equation here. We have And so here, of course, sodium hydroxide solid would be less entropic than the ions in solution, because now the ions spread out the energy of that sodium hydroxide formula unit. So now it's more spread out, it's more entropic. So when you dissolve a salt in solution, when you go from a solid to aqueous species, this generally increases the entropy. But there are exceptions that we'll talk about in just a moment. Likewise, if you rewrote the equation like this and you added water, technically you wouldn't add water, but let me try a different one. So now if we wrote something like this is a better example. So let's say we have methanol liquid and we put it in a solution with water, we get methanol aqueous. So again, it doesn't break apart into ions, but we have liquid and we have aqueous. And so here, the intermolecular forces at play in methanol are hydrogen bonding. The intermolecular forces at play when you put methanol with water, for example, to make it aqueous, are still hydrogen bonding. So what happens is that since the intermolecular forces present in the liquid and in the aqueous form are very similar, there's only a very slight increase, if any, in the entropy of the aqueous state when you start from a liquid state. Because again, the intermolecular forces that occur in the pure liquid are very similar to those that occur in the solution with methanol, for example. So there's very little change in the entropy. Very little, like very slight change in entropy. So in that case, they're almost the same. Now with metal cations, here we have a group 1 salt, and we have it in aqueous form and in solid form. So salts with very large cations, namely like your group 1 cations, the aqueous is more entropic than the solid state. So when you dissolve sodium chloride in water, it disperses the energy, making it more disordered. However, in D, the difference between C and D is in D, we have a very small, highly charged cation, cobalt 3+. So when you have very small, highly charged cations like your transition metals, like your group 13 metals, so those ions from those groups, they're very small, very highly charged. When you put them in solution, they actually become more ordered than in the solid state. So for those small, very highly charged ions, again, these are things like transition metal cations, group 13 cations, maybe some of the heavier group 2 cations, the solid is more disordered than the aqueous, because what happens is when you put that small cation in solution, it gets immediately surrounded by water molecules. So there's a lot of order associated with the ion in solution. So therefore, the aqueous state would be more ordered than the solid state. So again, that's the difference. So big ions like your group 1 cations, you put them in water, they become more disordered. Whereas your small, highly charged cations, when you put them in water, they become more ordered. So the solid state is actually more disordered than the aqueous state. Now in E, you notice that we have 2 elements in the same group. So when you're comparing elements in the same group, the further down the group you go, the more energy levels you need. The more energy levels you need, the more disordered the element is. So you would look here to see which one is further down the group. Is it indium? Is it aluminum? In this case, indium is lower than aluminum, so indium would be more entropic than aluminum. Next, we have 2 molecular compounds. And when you have 2 molecular compounds, generally what you're looking for is which one has the greater molar mass. So the greater molar mass usually tends to more disorder in the molecule. And so here when we look at these, you see the only difference is one has 3 hydrogen, one has 2 hydrogen, and a bromine. So bromine has a larger molar mass than hydrogen, so you can see that the one with bromine would have the greater molar mass, aka the more disorder for that molecule. And so these would be the ones that would be more entropic in the pairs. So moving on, now we're going to look at, can we predict the sign of delta S just by looking at the reactants and the products. So based on the reactants and products, it'll give you some insight on whether or not delta S could approximately be positive or delta S is negative. And one way to do that is to follow the moles of gas that we start with and the moles of gas that we end with, because moles of gas is a very good indicator of entropy. So if we start on the reactant side with gas and we have the product side with gas, if the product side has more moles of gas than the reactant side, then delta S would be positive, because the more moles of gas you have on the product side, the more dispersed the energy is, so it's going to be a positive delta S. Likewise, if you have more moles of gas on the reactant side than the product side, that means that your system compressed, so the energy is not as dispersed, so therefore delta S would be negative. So that's one way to look at it, is the gases. Also, if there's no gas present, then you have to look at aqueous versus solid, or aqueous versus liquid, solid versus liquid, etc. So in the first one, we have the synthesis of calcium carbonate. Notice here that with the reaction, we have 1 mole of CO2 gas on the reactant side, and there are no moles of gas on the product side. So we go from having 1 mole of gas on the reactant side to 0 moles of gas on the product side. So here delta S would be negative. So the products are less disorder than the reactants. Now you may ask, well, what happens when you have the same number of moles of gas on both sides? Then you have to look at maybe the molecular structure of the gases, or look at anything else that's on the reactants or product side. Next, in B, we have 2 moles of gas on the reactant side, and we have 3 moles of gas on the product side. So since the product side has more moles of gas, this delta S would be positive. In C, we look at the reactant side, we have a total of 9 moles of gas. So 4 ammonia gaseous molecules, 5 oxygen gaseous molecules. On the product side, we only have 4 moles of gas. So notice that H2O is a liquid. Now, if H2O was a gas, it would change things, but in this case, it's a liquid. So since the reactants have more moles of gas, here delta S would be negative. In D, we have 1 mole of gas on the reactant side, 0 on the product side. So this again, delta S would be negative. Now in E, you see that we have, on the reactant side, we have no gas, we have a solid and a liquid. On the product side, we have an aqueous and 1 mole of gas. So the fact that there's no gas on the reactant side and we have a solid and liquid versus a gas and aqueous, here delta S would be positive. And then lastly, we have a solid ammonium nitrate. We get the aqueous species. So here a solid, very confined. Ammonium is a very large cation. So when you go from a solid to aqueous, the energy gets more dispersed. So here delta S would be positive. So again, if you have gases present, it's very easy to approximate the sign of delta S. Now looking at some calculations involving delta S. So delta S is a state function. And what does the state function mean? It means to find the delta S of reaction, it would be the sum of the molar entropies of products minus the sum of the molar entropies of reactants. Now here we have an equation similar to the equation we saw on the previous slide. One of them, N2O yields N2 plus O2. We have the delta H of reaction. We want to calculate the delta S of universe in joules at 275 Kelvin. And the delta S of universe is the sum of the delta S of system plus delta S of surroundings. And if the delta S of universe is greater than 0, it's spontaneous. So based on the value of delta S universe, we'll be able to determine whether the reaction is spontaneous. And then we can then calculate, see at which temperature, if any, the reaction goes from spontaneous to non-spontaneous or non-spontaneous to spontaneous. So if you remember in the previous problem, we predicted the sign of delta S to be positive, if you remember from the previous. So when we calculate this delta S of system, we should get a positive value. Now again, delta S of system is equal to the sum of the molar entropies of products multiplied by their coefficients minus the sum of the molar entropies of reactants. And so since we have an absolute 0 temperature, unlike heats of formation, everything has a molar entropy associated with it. Even elements in their pure form, pure stable form, have a molar entropy associated with it because we have a 0 point for molar entropy. At 0 Kelvin, we have a pure crystalline solid. So with that said, we would look up in the table the molar entropies of our reactants and products multiplied by the coefficients, and we get delta S of system is about 4.6 joules per mole Kelvin. Now notice it's only slightly positive, but it is positive like we predicted. Now to find the delta S of surroundings, it's the negative of the delta H divided by T. So we have a negative delta H, negative 164.1. Two negatives make a positive. And notice that I converted the delta H to joules. So you either got to convert delta H to joules or delta S of system to kilojoules. But since we wanted the answer in joules, I converted delta H to joules. So now we have the delta S of system, delta S of surroundings. We add these two together, we get a positive 603 joules per mole Kelvin. So in B, is this reaction spontaneous? Since delta S of universe is greater than 0, the answer is yes. Now you may be asked, in a problem, at what temperature will it go from spontaneous to non-spontaneous? And so what we have to do is we have to set delta S of universe to 0. So we know what delta S of system is. We know what delta H is. We're going to solve for T. So again, anytime it asks for a temperature at which it goes from spontaneous to non-spontaneous, you're going to set delta S of universe to 0. And we're going to solve for T. So we put in the delta S of system, we put in the delta H in joules. We're going to solve for T, so we got to move 4.6 to the other side. Now we can rearrange T and we get this. So at this point, this should be a red flag here because the temperature that we get will be negative. And why is that strange? Is because Kelvin can only be greater than or equal to 0. So if it's negative, it's never going to be possible. So the fact that this temperature, to make it non-spontaneous, is going to be a negative Kelvin, which is cannot be, then you would say it's going to be never spontaneous, or you would have put NA as the answer. So again, whenever your result is a negative temperature, that's an automatic flag that says, hey, this can never be, in this case, non-spontaneous, any temperature. So it's always going to be spontaneous. Now the last question deals with another type of thermodynamic property called Gibbs free energy, because as we see in chemistry, when we look at delta H, reactions are endo or exothermic. When we look at entropy, reactions can be disordered or more ordered. So there should be a way to determine the spontaneous or non-spontaneous of a reaction. And the way we do that is through Gibbs free energy. So Gibbs free energy is the difference between the enthalpy of a reaction and the entropy of a reaction, given this equation here. So by knowing the signs of delta H and delta S, we know that we can determine then the sign of delta G. And just to remind you that delta G, when it's less than 0, it's a spontaneous process, reaction. If delta G is greater than 0, it's non-spontaneous. And if delta G equals 0, it's at equilibrium. So again, even with delta G, if you're ever asked at what temperature does this reaction become spontaneous to non-spontaneous, vice versa, what you would do is you would set delta G equal to 0 and solve for T. So now we need to determine whether or not this reaction is going to be always spontaneous, sometimes spontaneous, or always non-spontaneous. So we have to look at the signs of delta H and delta S. So delta H is going to be positive because heat is a reactant. Delta S is going to be negative because you see we have more moles of gas on the reactant side versus the product side. So since there's more moles of gas on the reactant side, delta S is negative. So now when we plug in these values, so delta G, we have a positive delta H. Now we have a minus T delta S. So since delta S is negative, this is going to be a positive T delta S. So notice here that your T delta S component is always going to be positive. Delta H is always positive. So here, delta G is going to be positive at all temperatures. So since it's positive at all temperatures, the answer to this would be it's always non-spontaneous. Because there will be no temperature at which you can make delta G negative. Because remember, Kelvin cannot be negative.